Neutron stars are among the most extreme objects known in the universe. They are born from the violent death of massive stars, when a supernova explosion compresses the stellar core so intensely that matter itself changes form. During this collapse, gravity becomes so powerful that protons and electrons are forced together, merging into neutrons. What remains after the explosion is a neutron star, an object only about 20 kilometers in diameter, but containing more mass than our sun. To understand how extreme this is, imagine compressing the entire mass of the sun into a sphere the size of a city. The result would be a neutron star. The density is so incredible that a single teaspoon of neutron star material would weigh billions of tons on Earth. Gravity at the surface is unimaginably strong. If a person could somehow stand there, which is impossible in reality, the gravitational difference between their head and their feet would be so large that their body would be stretched and crushed instantly. Time itself behaves differently in such intense gravity, slowing slightly relative to observers farther away. Yet the real mystery of neutron stars lies not on the surface, but deep inside them. Scientists believe neutron stars are layered, with each layer containing matter in increasingly strange and exotic states. The outermost region is called the crust. Despite the name, this crust is not fragile like the crust of Earth. It is incredibly strong, perhaps billions of times stronger than steel. In this region, atomic nuclei are packed together in a dense lattice, surrounded by a sea of highly energetic electrons. Under these conditions, atoms no longer behave like they do on Earth. As you descend deeper into the crust, pressure increases dramatically. The atomic nuclei begin to form and merge together. Instead of remaining spherical, they stretch into unusual shapes. Physicists have nicknamed these shapes nuclear pasta because they resemble spaghetti strands, lasagna sheets, and other complex structures. These bizarre configurations arise from a delicate balance between nuclear forces pulling matter together and electrostatic forces pushing it apart. The result is one of the strangest solid materials in the known universe. Beneath this crust lies the outer core of the neutron star. Here the pressure becomes so intense that atomic nuclei completely collapse. Matter transforms into a dense fluid composed almost entirely of neutrons. This neutron fluid is believed to behave as a superfluid, meaning it flows with almost no resistance. Superfluids are known on Earth in laboratory experiments with liquid helium, but in neutron stars the phenomenon occurs on an enormous scale. The superfluid interior may form swirling vortices that regulate the star's rotation. When these vortices suddenly rearrange themselves, the neutron star's rotation rate can change abruptly. Astronomers observe these events as pulsar glitches, tiny but measurable changes in the rotation speed of pulsars. Pulsars are rapidly spinning neutron stars that emit narrow beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like the light from a lighthouse. When the beam crosses Earth, we detect a pulse of radiation. Some pulsars rotate dozens or even hundreds of times per second. Their regular pulses are so precise that they rival atomic clocks in stability. These cosmic clocks allow scientists to measure tiny changes in rotation that reveal clues about the hidden interior of neutron stars. While the crust and outer core of neutron stars are already extraordinary, the greatest mystery lies even deeper in the inner core. At these depths, the density becomes so extreme that it may exceed the density found inside atomic nuclei. Under such immense pressure, the structure of matter may fundamentally change. One possibility is that neutrons themselves begin to break apart. Inside ordinary matter, neutrons are made of smaller particles called quarks. These quarks are normally locked tightly together by the strong nuclear force. But in extreme conditions inside a neutron star, that confinement may break down. If that happens, the inner core could contain a new phase of matter known as quark matter, a density of free quarks moving through space. Some physicists believe that an even stranger form of matter could exist there, called strange matter. In addition to the up and down quarks that make up normal protons and neutrons, strange matter would include strange quarks, forming a stable combination of particles not normally seen in everyday matter. If strange matter truly exists and is stable, it could represent a completely new state of matter in the universe. However, scientists cannot yet confirm this idea. The conditions inside neutron stars are so extreme that we cannot recreate them on Earth. Instead, researchers rely on indirect observations to study these mysterious interiors. One of the most powerful new tools is the detection of gravitational waves. When two neutron stars spiral toward each other and collide, they produce ripples in space-time that travel across the universe. These ripples carry information about the structure of the colliding stars. By analyzing the shape and strength of these gravitational waves, scientists can estimate how easily neutron stars deform during collision. This property, known as tidal deformability, provides clues about how stiff or compressible neutron star matter really is. These observations allow researchers to narrow down the possible models of what lies inside the stars. Neutron star collisions also play another important role in the universe. During these violent mergers, enormous amounts of neutron-rich material are ejected into space. In the extreme heat and pressure of the collision, heavy elements are forged through a process known as rapid neutron capture. This process is believed to create many of the heaviest elements in the periodic table, including gold, platinum, and uranium. In a very real sense, the precious metals found on Earth may have originated in the catastrophic collision of neutron stars billions of years ago. This means that studying neutron stars does not only reveal the behavior of extreme matter, it also helps explain the cosmic origin of elements found on our own planet. Despite decades of research, neutron stars still hold many unanswered questions. Scientists continue to investigate how massive a neutron star could become before collapsing into a black hole. They're also trying to determine exactly how matter behaves at densities far beyond those achievable in laboratories. Future observatories may provide new answers. More sensitive gravitational wave detectors, improved X-ray telescopes, and advanced radio arrays will allow astronomers to measure neutron star properties with greater precision. Each new observation brings us closer to understanding what truly exists inside these extraordinary objects. Neutron stars represent one of nature's most extreme laboratories, where gravity, quantum mechanics, and nuclear physics collide. They are tiny compared to most astronomical objects, yet they contain immense amounts of matter compressed into a volume barely larger than a city. Within them may exist forms of matter that have never been observed anywhere else. By studying neutron stars, scientists hope to uncover the deepest laws governing matter and energy. These stellar remnants are not merely the aftermath of stellar death. They are gateways to understanding the fundamental structure of the universe itself.